Hello, everyone. Thank you for tuning in to my virtual presentation. My name is Sierra Hypogene, and I'm excited to talk about the results of my master's thesis. This thesis would not have been possible without the funding from the Northern Rocky Mountain Annual Small Grant. So at the University of Kentucky, Dr. Benjamin Tobin and I have spent the last 2 years investigating hypogene speleogenesis in the Grand Canyon, using a combination of observational, mineralogical, and geochemical methods from the Bopper Cave system. Now, hypogene caves have distinct morphologies and mineral suites, and this study uses a variety of methods to determine a mode of speleogenesis. So I'm going to walk you through the background, the introduction, and the methods to help frame my 3 questions for this study. Being 1, has hypogene speleogenesis occurred in Grand Canyon? If so, 2, what is the acid of dissolution? What is the source of the acid of dissolution? So beginning with my introduction and my study area, the Bopper Cave system is located on the north rim of the Kaibab Plateau within Grand Canyon National Park. And this cave is not easy to access. Here is a photo of the entrance with a human for scale. There's about a 200-foot rappel just to get into the lip of the cave or the mouth. Now the entrance is a couple miles away from the Colorado River, and it sits about 3,000 feet above the modern base level. So we're looking at an abandoned or relict hydrogeologic regime of Grand Canyon. And take note of the entrance across from the entrance to Double Bopper, which is separated by a major side canyon. We'll get into that in a little bit. So this is a conceptual diagram that I use to help frame my speleogenetic hypothesis and to help visualize the end member system of cave development in the Grand Canyon. The mainstream mode for cave development is where surface or meteoric water collects on the rims of the plateau and percolates downwards through faults or fractures before encountering the red wall limestone and discharging as a spring. Now, I hypothesize that the Bopper Cave system is a hypogene cave developed from sulfuric acid speleogenesis, where these hypogene fluids would migrate upwards through major faults and fractures before encountering that same red wall limestone. Hypogene speleogenesis is much less studied in the Grand Canyon than epigene speleogenesis, and hypogene speleogenesis has been proposed but never proven to exist in Grand Canyon before. Now, I've used the term the Bopper Cave system a couple of times, and most of you are probably familiar with Double Bopper. So I'm referring to the Bopper Cave system as what was once a fully integrated cave, but which has now been bisected by incision and erosion of the Colorado River. So Double Bopper Cave, the longest in Arizona, is shown here, about 40 miles in length. There are several other smaller karst features around it, and then also the larger Leandros Cave over on the left. We get entrances exposed directly across from each other, which indicate the cross-cutting relationship where the canyon cuts the cave. So in other words, Double Bopper, or the Bopper Cave system, is older than the Grand Canyon itself in the eastern part of the park. Now, the Bopper Cave system is classified as a network maze cave, and you can kind of get a sense of that just by looking at the plan view. There are several closed loops. They tend to have little relationship with the surface topography. These type of caves are formed from the simultaneous widening of all joints. They typically have a high discharge to distance ratio. Okay, moving on to the background, it's important to talk about the geologic setting in Grand Canyon to help frame my speleogenetic framework. Since the Grand Canyon is such a complex geologic setting, we're going to go through the hydrostratigraphy, the lithology, and the structure of my study area. So beginning with the hydrostratigraphy, these are the 4 hydrostratigraphic units within the Grand Canyon that comprise other formations. The hydrostratigraphic unit of interest for this study is the Redwall Moab Aquifer, which I'll refer to as the RM aquifer. It's highlighted in blue here. Not only is it the major cave forming unit, but it's also very regionally important. It's the only source of fresh drinking water for millions of Grand Canyon's annual visitors, the various tribal nations in the region, and wildland firefighters. And within the Redwall Moab the RM aquifer hydrostratigraphic zone, we have the Redwall limestone itself, which is comprised of 4 other members. The Mooney Falls member is the member of interest. It has the largest concentration of caves in the Grand Canyon, partially due to the several different episodes of karst events, starting with early exposure in the Mississippian, which formed a widespread paleokarst breccia, which we'll talk a little bit about later. So now that we know about the Redwall limestone and the RM aquifer, I want to talk a little bit about fault displacement of the Redwall limestone in Grand Canyon. On the left is a picture of a cave formed in the Redwall limestone that's at the level of the river. And on the right is the Bopper Cave system, a couple entrances to the Bopper Cave system. Although this portion of the Redwall limestone has been juxtaposed 3,000 feet above the Redwall limestone on the left. So we have major faulting, which is displacing units across the Grand Canyon. And where those units are at the level of the river, we have the modern actively conveying caves, which is sourcing water from the rims. And on the right, we have caves 3,000 feet above the river. These are relict features of an ancient hydrogeologic regime. So through the lens of cave systems, we can study the evolution of an aquifer from the ancient to the modern. Now, moving on to modern spring water geochemistry, this is extremely important for my research because today we actually see modern hypogene springs discharging at several areas within the canyon. So these have high strontium, high carbon dioxide, sulfate, they're high in salinity, they've got higher temperature, and they're migrating upwards through faults and fractures before encountering the Redwall Muav aquifer discharging as springs. And we do see a lot of mixing in the system where our lower world and our upper world hypogenic and epigenic fluids are mixing. But the important thing being that if we're looking for suspected hypogene caves, which are really old, this is good evidence to support. So we have modern hypogene springs, so it's good evidence to support that processes that were happening today may have also happened in the past. Uniformitarianism in geology. So moving on to the background for structure, which refers to faults and fractures, an important part of my research was to identify which structures may have sourced the speleogenetic fluids. And this was sort of a different study. So I'd like to just present the preliminary results from this paper that I published with Dr. Benjamin Tobin, which outlines that the sources of the speleogenetic fluids are likely from the halogen or the Leandris faults shown on this figure. And we used a combination of linear regression to identify relations in passage size and proximity to major faults. So it makes sense that we would have these large faults conveying speleogenetic fluids. Also, I'd like to point out how the Leandris fault completely intersects Leandris Cave. And also, this is a really good viewpoint of how entrances are juxtaposed across from each other before incision of the Colorado River would have eaten away the cave system right here. So in short, we've identified that the halogen or the Leandris fault were the likely sources of speleogenetic fluids using GIS and statistics. All right, moving on to the methods. We began with sampling and field observations because the cave lacked a baseline geologic description. Cave survey began in 2009 when the cave was discovered, and cavers have done a great job describing geologic features, but there was no comprehensive assessment of the geological features in the cave. So we began with the baseline description, also incorporating X-ray diffraction to identify the various colorful minerals in the cave. And lastly, I used stable isotope geochemistry of sulfur isotopes to determine the source of the speleogenetic fluids. So we sampled in October of 2022, I believe. I had several different areas within the cave I was interested in sampling. I wanted a large spatial distribution for all samples taken, but access to the cave was limited by our availability to only go in there for the daytime. We weren't camping. So my spatial coverage isn't as full as I would like, but we ended up with 35 gypsum samples and 40 unidentified mineral samples. Field observations included identifying anything with geomorphology, speleogenes in the cave, the types of sediments, and stratigraphy, anything that could help us identify the speleogenetic origins of the Bopper Cave system. And this is the machinery we use to collect diffraction data. I'm going to show you what diffraction data looks like in just a moment. But when I refer to X-ray diffraction, this is the machinery that we use to collect the data. So here is an example of X-ray diffraction. We collect this based off of reflections from crystallographic facies. It's almost like a crystallographic fingerprint, which can help us identify several different minerals in a single sample. Where in looking at this figure, the x-axis is the angle to theta, and then the y-axis is the count. The black line is my sample, and the blue line is the standard. So this is one of the samples that I used to show that we have gypsum in the gypsum flower. So just an example of how diffraction data works, collected from one of these gypsum flowers. So I was able to identify 11 completely unknown minerals to exist in the Bopper Cave system. 22 samples were identified in total, and I'm going to go through these in the results section next. Lastly, I use water-soluble sulfate stable geochemistry isotopes to determine the source of the sulfate precipitating fluids in the Bopper Cave system. Now, isotopes are atoms of an element with two different sets of neutrons. Now, we measure the ratio of one isotope to another using a stable isotope ratio mass spectrometer. That's a mouthful. But in other words, we can use isotopes to tell the origins of fluids. All right, that wraps up the methods, and we'll move on to the results and the discussion. We use a variety of approaches to answer my first question: has hypogene speleogenesis occurred in Grand Canyon, which includes morphology, speleogene development, sediment characterization, and minerals, since hypogene caves do have distinct morphologies and minerals which have been described in other cave systems. So right off the bat, looking at morphology, the passages are really big. These are big phreatic borehole or tube-shaped passages. And the shape of the cave system can help us understand the conditions under which it was formed. In this case, these type of passages are formed in the phreatic zone underwater. We also have large lens-shaped passages, and even the smaller passages in the cave have the same sort of size, which again contributes to the phreatic nature of the cave. The cave has very large horizontal development with little vertical development. Most of the cave is constrained within the Mooney Falls, and like I said, just not a whole lot of vertical development. There is a complete lack of vadose morphology. This is a picture from Kentucky. Your classic epigenic cave system. Lots of vadose imprinting in Kentucky. We have a complete lack of canyons with meanders, dome and pit complexes, or dendritic style passages in the Bopper Cave system. Okay, so moving on to speleogenes. Speleogenes is what is taken away by solutional aggression, creating various different bedrock forms. And again, hypogene speleogenes are distinct from epigenic speleogenes. And so this figure from Klimchuk shows a variety of different features you would expect to see in a hypogene cave. We'll come back to this figure several times. But we have rising wall channels, which is characterized by a rising chain of cupolas, a dome pit right here, a feeder for the convection, and then ceiling half tubes. So comparing this to images from inside the Bopper Cave system, we have a lot of these features. This is an example of a room full of cupolas. There are hundreds in this picture. And if you can't see, they're the small divots, the spoon-shaped features along the walls. Bell-shaped dome features, and all of these speleogenes are formed from condensation, corrosion, from buoyancy currents. The air was basically so acidic from the hypogene fluids that it just eats away at the cave walls. These are very abundant throughout the Bopper Cave system, and these cupolas can be mistaken for scallops, but scallops show unidirectional flow. And again, we see the cupolas demonstrated here as just texturing of the wall. Here's a good example of rising sets of coalescing cupolas. This is described as being diagnostic from Klimchuk. An isolated ceiling dome. This is also associated with condensation corrosion, and it may be formed above a feeder feature. So this is not an upper level passage. This is basically just a hole poked into the ceiling. And that's why exploration is so important and citizen scientists, so that we can make these concrete scientific observations from cavers who are willing to climb into the ceiling to see what goes beyond or what doesn't. Here's a picture of an isolated ceiling dome. Now, in terms of vertical development, we don't have a whole lot, but there is one fissure, the only known occurrence of cave formation to go down into the Thunder Springs member of the Redwall limestone. So it's not common to have caves forming in this zone, and this fissure passage is the only one like it in the Bopper Cave system. Fissures that are like this in other hypogene caves are considered feeders, where the source of the acid may have migrated upwards. And I know I already told you that we identified several different faults as potential feeders, but this is another one of those. It's not marked as a fault, but it is a major vertical conduit in the cave, and it could likely be the source of the speleogenetic fluids. And here is that fissure feeder shown in Klimchuk's figure. And lastly, we have a ceiling half tube, again formed from rising flow and dissolution. And this is a beautiful picture, lots of gypsum flowers. You can see the ceiling half tube and the lens-shaped passages. Half tube shown right there. We basically just have really corrosive gases that create lots of different speleogens. So all in all, we do see a lot of hypogene speleogens. Now, moving on to cave sediments. The sediments in the cave were entirely autochthonous, meaning that they are produced locally rather than from afar. There's nothing fluvial, nothing brought in by water, nothing coarse-grained, aside from a singular area with cave pearls. Now, epigenic caves have more connection with the surface, and so this further reiterates that this is a hypogene cave. These are fine-grained powders. Sometimes the powders form into blocks, and they are laminated, which means we have a very slow-moving environment that settled these sediments out. So the next logical step was to identify these cave sediments. So these bright yellow sediments I first thought were uranium. A little bit scary, but would have been very interesting because we do have uranium in the Grand Canyon. And here's another example of a coating of the yellow substance. This was identified as goethite and hematite. Many of the red, orange, brown, and yellow powders in the Bopper Cave system are likely iron oxides and hydroxides, like these were identified as. And iron oxide's counterpart is manganese oxide, not magnesium. These are fluffy coatings and blocks, and they don't necessarily indicate a hypogene origin for this cave, but they do tell us about the environment of deposition. So when you're in the phreatic zone with little oxygen, any fluctuation in the water table is going to precipitate out iron or manganese oxide, since they are EH and pH redox indicator elements. All right, so we've got all these oxides that would have settled out in the deep phreatic zone. And then we also have these pretty green crystals formed in a vein above the green door. Now, these were identified as malachite and also massive calcite, along with some goethite. These had to have been formed from post-speleogenetic fluids, since the fluids that created the Bopper Cave system would have dissolved these away had it been introduced. Now, these deposits can be thermal or hydrothermal, further suggesting and supporting a hypogene origin. In other words, the fluids that precipitated this copper most likely had to come from below. So that tells us we have some hypogene fluids in the system. Here's the zone of copper mineralization. Like I said, we've got massive calcite, malachite, goethite, and probably some chrysocolla, and then some nice spar on the right as well. All right, now in summary, we have phreatic morphologies, we have many hypogene speleogenes, autochthonous cave sediments, we have phreatic minerals and potential hydrothermal minerals. This all suggests that hypogene speleogenesis has occurred in Grand Canyon. Which leads me to my next question, which is going to be, what is the acid of dissolution here? Now, more work is needed to understand these hypogene fluids, but as of right now, hypogene caves can be formed from sulfuric or carbonic acids, but we also use a combination of stratigraphy and mineralogy to answer this question. Now, gypsum is the most common byproduct of sulfuric acid speleogenesis, and boy, do we have a lot of gypsum in the Bopper Cave system. We've got gypsum swords, gypsum hair, gypsum needles, gypsum grass, as well as millions of gypsum flowers, the best I've ever seen. This is a map showing the distribution of gypsum, and I think it's actually underrepresented by this figure, but it gives you a sense of the sheer amount of sulfate in the system to create gypsum. Again, beautiful gypsum flowers. Now, one really interesting observation that I took note of is that there seems to be a preferential extrusion of gypsum from certain layers within the Mooney Falls member. Now, the layers that are brecciated are the ones that are extruding gypsum flowers. So we have interfingered, brecciated, and unbrecciated rocks. And in the ceilings of these passages is where, in the brecciated zones, the gypsum flowers are preferentially extruding. Another great examples of the gypsum flowers and also some of the breccia in the ceiling up here. Again, another picture of breccia blocks. You can see the intact block of limestone here, the breccia matrix, and then the beautiful corkscrew gypsum flowers. Okay, moving on to gypsum rinds. These form where hydrogen sulfide diffuses into the cave air as the water table drops. The buildup of the sulfate from the acid plus the calcium from the carbonate rock is great enough to force gypsum to reprecipitate on the bedrock surface. This is considered diagnostic of hypogene caves, and specifically sulfuric acid hypogene caves. This is distinct from evaporative gypsum, so it's kind of like a rind that coats the walls. Now, moving on to other sulfates that we identified in the Bopper Cave system, we've got epsomite in this little green nodule that is coating the cave wall. Now, these sulfates I'm about to identify are commonly found in many different epigenic and hypogenic cave systems, but the sheer amount that we have and the different coloration too is not normal for epigenic caves. This Jolly Rancher green gypsum flower is also likely epsomite. We also have moralobite, bernardite, and most exciting, jarosite and nitrojarosite. So jarosite forms in highly oxidative and acidic environments. It can form from sulfur-bearing solutions or the oxidation of pyrite. Now, nitrojarosite is an extremely rare cave mineral, only described in one other cave in the world in South Africa. And so immediately I'd like to get more data on this to further identify the concentrations of jarosite and nitrojarosite. More work is definitely needed, but it's a very exciting find, especially the fact that I found it like in this yellow powder that was coming from a hole in the ceiling. So again, I'm glad it's not uranium, but it's super exciting to find jarosite. Now, here is the strangest sulfate. This formation here has never been described in any other hypogene cave. While it looks like boxwork, it's not boxwork. It's stringy, microbial looking, and this was referred to as gypsum foam, as iron foam because of its coloring, but which I have identified to just be calcite and gypsum, and so we are newly dubbing it gypsum foam. Now, I have no data to support whether or not there is microbial activity in the BCS, but there are abundant biological communities in caves formed from sulfuric acid speleogenesis in other parts of the world. Um, Further work is needed to look at thin sections, which will be coming in the next publication to tell whether or not it's biogenic. We also had some anhydrite and quartz, and I'm not quite sure how to describe the quartz yet. Like I said, further work is needed. All right, this was an exciting find. We've got hydromagnesite that we found in this deep white powderous area. Um, in this room here, the white powder is, I mean, I'm not completely sure how thick it is, but I mean, over 12 inches, certainly in some areas. And hydromagnesite is a common forming mineral in moon milk, where moon milk is a biogenic mineral produced by microbes. And hydromagnesite likes to form in highly evaporative environments. So this was an interesting find. I'm not sure if there has been another cave with this thickness documented for hydromagnesite. Okay, corrosion residue. Multicolored sediments of iron and manganese oxides and clays. Now this stuff is really, really soft. I can practically just poke my finger through the wall there. Now it's described in other hypogene caves as a sulfuric acid alteration of clay, which produces iron and manganese oxides and hydroxides. Some studies show that corrosion residue deposits are biogenic, which are the result of redox reactions. Subsequently, oxidation reactions in the weathering zone can serve as an energy source for microorganisms such as iron oxidizing bacteria. So this corrosion residue is really interesting, and once again, we probably need a little bit more research to be able to identify whether or not it's biogenic. But in other cave systems, we see that it is biogenic. All right, so what is the acid of dissolution? Using the combination of the identification of sulfates and morphology, we have identified that this is likely a sulfuric acid speleogenesis cave, or SAS. So one of the biggest implications of my research really is now that I can call the Grand Canyon sassy and the Bopper Cave system sassy. Okay, so moving on to the third question, what are the sources of sulfuric acid? This is where I use stable sulfur isotope geochemistry, which acts as a geochemical fingerprint. So for the possible sources of sulfur, we've got a couple different options here. We've got evaporites, we've got a magmatic or volcanic origin, sulfide oxidation, in other words, pyrite can oxidize, and then hydrocarbons can also supply speleogenic sulfur. So this is a plot which shows the isotopic concentrations of several different sources, and then also the concentration of the gypsum flowers that we see in double bopper. So I'll start with what's highlighted in orange, the double bopper gypsum samples, which range from about 0 to -15 per mil. And again, these measurements are just looking at the ratio of one sulfur isotope to another. So the most common source for sulfur in caves, especially epigenic caves, are from evaporites or salts. But these salts range very isotopically light, from around +10 to +20 per mil. So it's definitely not from evaporites or salts in overlying or underlying units. Now, modern Grand Canyon springs have a pretty wide range of values, and that's interesting because what we're probably seeing is that mixture of hypogenic and epigenic fluids, and we're seeing that signal in the isotopic range. Now, some magmatic sulfur from Western Grand Canyon has been identified to range as low as -5. So here we have some good overlap with the double bopper gypsum, our first good candidate. But then moving further, we have bacterial sulfide oxidation and we have bacterial sulfate reduction. And both of these variables have pretty large ranges in the data. And what this is telling us is that bacterial sulfide oxidation and reduction can essentially alter the isotopic concentration of a sample. So this isn't disproving or proving that we have bacterial oxidation or reduction in the cave, But since we do have good overlap, it's quite possible that some of the sulfur in the gypsum flowers may have been altered through microbial processes. The Guadalupe hydrocarbon caves, this includes Lechuguilla and Carlsbad. These range more negative than the gypsum from my samples. And so I don't have any hydrocarbon data from the Grand Canyon, but the flow path from the hydrocarbons to the cave would be difficult. In addition to looking at the hydrocarbon data from New Mexico, it's likely not hydrocarbons that source the gypsum in Double Bopper. Now, lastly, we have Chuar sulfides. This has an extremely large range of values. Now, sulfides referring to pyrite, since pyrite can oxidize and form into gypsum later on. The issue with pyrite is that we probably have a mass balance issue. There's likely not enough pyrite to be sourced in the Chuar to account for such large quantities of sulfate in the Bopper Cave system. Okay, now looking at the modes for sulfuric acid speleogenesis, the pyrite may have come from shales, which I showed down in the Grand Canyon supergroup, along with those hydrocarbons, whereas magmatic sulfur can be sourced from far away and migrate its way up those faults and fractures. Sorry, guys, I think I just muted myself there for a second. Okay, moving on to the importance for this work. First of all, the identification of other hypogene systems and their implications for karst aquifers, better understanding of the evolution of the ancient and the modern RM aquifer, and also storage potential. So, contributing to the knowledge of other hypogene caves and karst aquifers, my hypothesis was that hypogene caves exist in Grand Canyon. Um, Only in the last century has hypogene speleogenesis been considered a fundamental karst process. Hypogene caves have historically been misinterpreted, so new research and identification is critical for adding to the knowledge base. So we can better understand places like Jewel Cave, Wind Cave, Lechuguilla, Carlsbad, and now Double Bopper. This map sort of shows different regions which have known hypogene caves, and my research is adding a star to that. And so one day I think we're going to see sort of a continuum across the US of hypogene caves with different origins. Okay, I know I just hit my 30-minute mark, so I'll wrap this up pretty quick. Okay, so looking at the evolution of the ancient RM aquifer and the modern RM aquifer, modern spring water geochemistry tells us that hypogene speleogenesis is likely continuing today. The concept of uniformitarianism, processes that happened in the past are happening today. We have modern hypogene fluids at the level of the river. Again, I want to remind you that this aquifer is the sole source of drinking water to Grand Canyon National Park, tribal nations, and wildlife. And it's also important to note that a changing climate may cause fluctuations in the ratio of hypogene to epigene signals. Now, hypogene waters do degrade water quality, so understanding the source and the character of these hypogene fluids is also critical for water quality. And lastly, the third key piece of importance for my research is the storage potential of hypogenic versus epigenic components. We're used to thinking about storativity in terms of matrix porosity, fractures, and conduits. But if I am correct that there are many hypogene systems in Grand Canyon, then the concept that there are these mega conduits that may exist within the Redwall limestone without an entrance to the cliff face may contribute to some of the storage component in the modern RM aquifer, something we should take into account. And with that, I would like to acknowledge the Northern Rocky Mountain Grotto for their support in my research, along with the various other donors. And I thank you for your time and your patience with me, and I will take any questions that you may have. Thank you.